Analog to digital conversion. Hi, my name is Steve Sanislow. The analog to digital conversion process can be difficult to understand, primarily because it's hard to visualize. Sampling an audio signal at 40,000 times per second is hard to envision. Measuring an audio signal voltage to within a millionth of a volt is beyond comprehension. Is all of this high-resolution digitizing really necessary? Is the human ear really all that sensitive to small changes in sound? To help visualize the sampling process, let's look at a very familiar but very slow-moving waveform, the waveform of the human heartbeat. Now let's superimpose a graph on top of that waveform. Each vertical line of the graph represents a sampling period. And this time, and in this example, we're sampling the heartbeat at a rate of 8 samples for every heartbeat. Now every time the heartbeat waveform crosses one of the vertical lines, which represents a sampling period, we're going to put a dot. And after we put all the dots in place and connect the dots together with a line and get rid of the background, we see the resulting digitized waveform of the heartbeat. It doesn't look very much like a heartbeat at all. So let's do this again. We'll take the heartbeat, we'll put a graph on top of it. This time we'll sample at twice the frequency as before. We'll sample 16 times per heartbeat. And once again we put a yellow dot on the heartbeat waveform every time the waveform crosses one of the vertical lines representing a sampling time. And when we connect all the dots together and get rid of the background, we see a waveform that is beginning to look a little bit more like a heartbeat. But the question is, how much faster do we have to sample that heartbeat waveform in order to get an accurate representation of the heartbeat waveform? To answer that question, you would have to take the heartbeat waveform and put it through a spectrum analyzer to look at the whole range of frequencies generated by a heartbeat. You would have to find the highest frequency, and that may be a frequency that's several kilohertz in frequency. Once you find the highest frequency, let's say it's 2000 hertz or 2000 times per second, you'd have to double it to find the Nyquist frequency. The Nyquist frequency determines how fast you're sampling, it determines the minimum sampling time required in order to accurately reproduce the waveform. So if the Nyquist frequency was 4,000 times per second, you would have to sample the heartbeat waveform 4,000 times per second in order to accurately reproduce its waveform. The same is true for digitizing audio, but with an audio waveform, the highest frequency the human ear can hear is about 20,000 hertz, so the Nyquist frequency would be in excess of 40,000 hertz. In other words, we have to sample an audio frequency 40,000 times per second or faster in order to accurately reproduce its waveform. Another aspect of analog to digital conversion is bit depth, and bit depth is all about dynamic range. What is dynamic range? Well, a pin drop is considered to be one of the quietest sounds that the human ear can hear. A whisper is 100 times greater than a pin drop. A conversation can be 100 times greater than a whisper, and loud television can be 100 times louder than a conversation. If we go to a concert, the sound that we hear at a concert can be 100 times louder than a loud TV. Bottom line, a concert could be 1,000,000 times louder than a pin drop. Bit depth gives us the ability to reproduce that wide range of sounds, from a whisper all the way up to something loud as the ear can perceive. And the commonly used bit depth in audio recording is 24, which yields a dynamic range of 16 million to 1. And if that sounds like a lot, consider that the threshold of hearing is 0 decibels. The threshold of pain is 130 decibels, meaning that the ear has a dynamic range of 130 decibels, or a trillion to 1 ratio, which represents a bit depth of 30. So we're not even near the limits of our hearing.